Hello students, this is teacher Lamesa, your calculus teacher. Welcome to week 17 session of our calculus class. During this week, we'll be discussing about relative rates of growth, which is in section 9.3 or chapter 9, section 3 of your textbook. Let's make a very quick review of the previous week lesson, which is about L'Hopital's rule. Hope you remember about that. Evaluate the limit of ln x over e to the power of x as x approach infinity. Remember to apply the L'Hopital's rule, where you have to differentiate both numerator and denominator until you get a certain limit. So the limit of ln x over e to the power of x as x goes to infinity is 0. Second example, try to have a look at this one also. The limit of e to the power of x over x cubed as x goes to infinity can be shown that it's going to infinity. The limit of x squared over e to the power of 2x as x goes to infinity is also infinity. 4. Limit of x squared over e to the power of 2x as x goes to infinity with the help of L'Hopital's rule also goes to 0. So what are we going to learn in this lesson in chapter 9 section 3 of our textbook? At the end of the lesson, you will be able to compare rates of growth, and you'll be also using the L'Hopital's rule to compare the growth rates of different functions. The end behaviors of the graphs of some special functions are going to be discussed in detail during this lesson. So you need to remember how the graphs of y equal to e to the power of x, y equal to x, and y equal to the natural logarithm of x behave for very large values of x. When we say very large value of x, as x goes to infinity. So let's see how the relative rates of growth for y equal to e to the power of x, y equal to x, and y equal to the natural logarithm of x compare as x goes to infinity. The blue colored graph is the graph of y equal to e to the power of x. It's an exponential function. And the red colored graph, or the linear graph, is the graph of y equal to x. And the green colored graph is a logarithmic graph, which is the graph of the natural logarithm y equal to ln x. If you see three of them, as x goes to infinity, all of them go to infinity, but all of them go to infinity at different rate. So we will be using these three graphs, or the end behavior of the graphs of the exponential and the linear graph y equal to x, and the logarithmic graph y equal to ln x throughout our lesson. Okay, for large values of x, if you have two functions f of x and g of x, it's the case that one of the function may grow faster than the other, or it may grow slower than the other. It's also possible that the two functions grow at the same rate. Let's say we have two functions f of x and g of x for a positive value of x which is sufficiently large. We say f grows faster than g, or g grows slower than f as x goes to infinity if the limit of f of x over g of x goes to infinity. This can equivalently be expressed as if the limit of g of x over f of x as x goes to infinity is equal to 0, it's also possible to say f of x grows faster than g of x. The other case is f and g are said to grow at the same rate as x goes to infinity if the limit of f of x over g of x goes to a certain fixed limit L, which is different from 0. Now let's have a look at an example that helps us to compare e to the power of x and x cubed for a very large value of x. Here is the question. Show that the function e to the power of x grows faster than x cubed for very large value of x. To show this, we have to find the limit of e to the power of x over x cubed, and our limit should go to infinity. It is this time that we say e to the power of x grows faster than x cubed. Okay, what we try to do is first we try to plug in a very large number in place of x in both e to the power of x and x cubed separately. If we do so, we will get an infinity over infinity type of indeterminate where we'll be forced to use the L'Hopital's rule. The L'Hopital's rule says we have to differentiate the denominator and the numerator functions until we reach in finding a very reasonable limit for the given expression. So the limit of e to the power of x over x cubed is an infinity over infinity type. So we have to differentiate both numerator and the denominator. That gives us e to the power of x over 3x squared. Again, trying to plug in a large number or an infinity in the place of x gives us infinity over infinity in the second step. Proceed again to differentiate because it is still an indeterminate form. The derivative of e to the power of x is itself. Of the denominator 3x squared is 6x. Again, plugging in a large value of x here gives you infinity over infinity. So continue differentiating each of the numerator and the denominator separately. You'll get the limit of e to the power of x over 6 as x goes to infinity. Now we have no trouble finding the limit. The limit of e to the power of x divided by 6 as x goes to infinity is infinity. So what does this tell us? It means e to the power of x grows faster than x cubed as x goes to infinity. Let's move on with another example. This time we will be looking at how the graph of the natural logarithmic function y equal to ln x compared with the graph of the linear function y equal to x as x goes to infinity. Here is the question. Show that the natural logarithm ln x grows slower than the linear function y equal to x. Okay, we can approach this question in two different ways. Ln of x grows slower than x is exactly the same as x grows faster than ln of x. We can either show the limit of ln x over x as x goes to infinity is 0, or the limit of x over ln x as x goes to infinity is infinity. Let's work on the earlier procedure. Let's see the limit of ln x over x as x goes to infinity. Plugging in x equal to infinity in ln x and x gives us infinity over infinity type of indeterminate. So we have to apply the L'Hopital's rule, where we have to differentiate ln x and x separately to get 1 over x and 1. It's clear that the derivative of ln x is 1 over x, and the derivative of x is 1. So we will get the simplified form of 1 over x over 1 is limit of 1 over x as x goes to infinity, which is obviously 0. So this tells us that the natural logarithm ln x grows slower than x. In the previous two examples, we have seen how two functions are comparing to the other, especially where one is growing faster or slower than the other. But in this one, we will be looking at two functions which are growing at the same rate. The question says, show that x grows at the same rate as x plus sine x. Here we have to take two functions, y equal to x, which is the linear function, and y equal to x plus sine x. This is the combination of two functions as x goes to infinity. To show that these two functions grow at the same rate, we have to follow the definition and try to find the limit of the ratios of the two functions, x plus sine x divided by x as x goes to infinity. If we are able to show that the limit of this ratio is a certain fixed real number L, which is different from 0, we can say that the two functions grow at the same rate. So to start finding the limit of the ratio x plus sine x to x, we can share the denominator x for x and sine x separately. So we can make it x over x plus sine of x over x. It's obvious that x over x is 1. So we have limit of 1 plus sine of x divided by x as x goes to infinity. Sine of x over x as x goes to infinity, as you may remember from our limit session at the beginning of the academic year, it is 0. So 1 plus 0 is equal to 1. So we have obtained a fixed real number L, which is equal to 1 as the limit of x plus sine x over x. So this proved that x plus sine x and x are growing at the same rate. Transitivity of growth rates. If f of x grows at the same rate as g of x as x goes to infinity, and g of x grows at the same rate as h of x as x goes to infinity, then we can say that f grows at the same rate as h of x as x goes to infinity. Let's look at this example to help us understand about the transitive property of the growth rate. Show that f of x is equal to the square root of x squared plus 4 and u of x is equal to 2 times root x minus 1 the whole square grow at the same rate as x goes to infinity. To show that f and g grow at the same rate, we can take the third function h of x and try to show that both f and g are separately grow at the same rate with h of x. Okay, now let's compare first f of x and h of x. We are trying to see how the growth rate of f of x compares to the growth rate of h of x for very large value of x. So to do that, we have to do limit of f of x over h of x as x goes to infinity. So replacing the expressions of f of x and h of x, will have limit of square root of x squared plus 4 divided by x as x goes to infinity. To easily find the limit of this expression, we can place x under square root by squaring the x in the denominator. That gives us x squared plus 4 over x squared, and the radical should go for the whole ratio expression. And that can simplify to the limit of 1 plus 4 over x squared as x goes to infinity. As x goes to infinity, it is clear that 4 over x squared goes to 0. So under the radical sign, we have 1 plus 0, which is the square root of 1, and the limit is 1. Now we compared f of x over h of x, and we found the limit as x goes to infinity is 1. This clearly tells us that f of x grows at the same rate with h of x. Next, let's do the same thing to know how the growth rate of g of x compares with h of x. So we have to do the limit of g of x over h of x as x goes to infinity. So we have limit of 2 root x minus 1 squared over x as x goes to infinity. We can put all of them under the same square, but to do that, we have to keep x under the square root, because we know that the square of root x is x. If you try to find the limit of the inner function inside the bigger bracket, you get limit of 2 minus 1 over x as x goes to infinity. As x goes to infinity, the expression 1 over root x goes to 0. So you will have only 2 inside the bracket, and 2 squared is 4. The limit of 4 as x goes to infinity is 4 because it's a limit of a constant. Okay, this proves that g of x grows at the same rate with h of x. So by the transitive property, we can show that the limit of f over g as x goes to infinity can be written as the limit of f over h times h over g. It's obvious that h can cancel with h, and you can simplify to f over g. As x goes to infinity, what happens? The limit of f over h is 1. We have seen it in the first limit. And the limit of h over g is 1 over 4. The product 1 times 1 over 4 is 1 over 4, which is a constant figure. So this proves that f of x grows at the same rate with g of x. With this, we come to the end of our lesson, which is section 9.3. See you during week 17 of our lesson next week. Bye.